Hello and welcome back to Precalculus, where we talk about function composition, one of the very important topics to build for calculus. Now, before we jump into function composition, let's talk about function combinations, which is something that it's more intuitive and I guess less important. Well, it's important, but um, it's kind of common sense thing. So function combinations or combination, how about combination of functions? And I'm going to flat out list not all of them, but most of them. So f plus g, you can add functions. F minus g, you can subtract two functions. F times g, you can multiply two functions. F divided by g with g different than 0, you can divide two functions. You can square a function, you can put the root of that function, and I was going to put 3 dots because it became boring. Now, what are these combinations? Well, if I write y equals 2x squared plus 3x, right? You can decompose this if you want to. You shouldn't, but you can. You can decompose this into f of x equals 2x squared and g of x equals 3x. And then f plus g will give you the y you had before. Do we ever do this? No, we never do this, right? But you can, right? So there are a lot of things in life you can do and you don't. So this is one of them. Now, it's sometimes helpful in computation to have the separate parts like this. It's also important in considering the domain of a function, but at large, we don't really care about it. So let me give you a couple of examples where we do care about it, and primarily it's like domain situation. So what is the domain of, let's say, y equals 3x squared plus 6 over x? So this is clearly composed with two different types of functions. Here is the function which is a polynomial, and here is the function that it's a rational function. Now, we know the domain is set of all possible input values. So you might go and say, can I plug anything for x? And the answer is no. There is one value that is going to break the entire equation. It's going
It can't
to,
be 0, right?
yes. See, 0 ruins it for everyone, right? That's like when you go to a party and there's a Karen there, right? It's like, oh my, why, right? There's always one. So you look at this and you say, you know what? The domain for this is negative infinity to positive infinity, meaning all real number. You can pick any x you want. Fraction, decimal, whole number, positive, negative, even, odd. I don't care which way you're going to classify your number. Rational, irrational. It doesn't matter. Any number you can possibly think of, any size, whatever goes in there, it's okay. But this one over here has a problem, right? This one is negative infinity to 0, union 0 to infinity. So that one has a restriction, right? Which is what I say, there's a Karen right here. X can't be 0, right? I want to see the manager. So the entire function suffers because of one idiot. That's how society works, right? And usually those are the most loud one and the dumbest one of everyone, right? So when you take a look at these functions that are combinations of multiple functions, each individual cell will have its own parenting function, its own shifts and everything, and its own domain. And in a case now here, you are going to have the overall domain to be the most restrictive one, because it's always the most restrictive one which governs the rules for everyone else. So you might be going, why do we have such a low speed limit? I mean, 65 miles per hour is ridiculously low speed. Ridiculously low. There are people that are comfortably driving over 100 miles per hour, professional racers, but whatever. But you also have people that are 80 years old on the same highway and their reflexes have left them 50 years ago, right? So they can't switch a lane for 15 minutes, right? You know, when you pass that ghost car, you just see the knuckles. You don't even see the head. You just see the knuckles on the wheel, on the steering wheel. So yeah, the speed limit is 65 on the highway, right? You go to Germany on Autobahn, no speed limit. Okay, right? They don't mess around. But you go 78 here, right? We just moved to Pennsylvania. It's 55. It's like even worse, right? So it's restrictive because there is one part of the whole machine that makes it restrictive. Another part to consider is you also heard the chain is as strong as its weakest link, right? So clearly, right, if you have one weak link in the chain, that's the one that it's going to snap. And the amount of stuff that you can lift or pull with that chain is exactly as much as that link can withstand. That one link. It doesn't matter that you have 10,000 other links there, right? And they're all 10 times stronger. Which is also interesting when people are buying computers. They go in and said, I have a processor that it's, whatever cores and blah, 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 blah. And then it has one component that is garbage. Yeah, computer has 10 components. Your computer is as fast, as strong as the slowest and worst component of all. So that's the bottleneck. I don't care if that is a processor or RAM memory or a hard drive or anything. Any one component in a computer can decrease the performance of the entire computer because that one is the bottleneck. So now you have a lot of examples here, right? And anytime you're looking at the domain, you will always look at the restrictive part and say, okay, so I understand that I can plug 0 in this term, but here is the Karen term, and that one is going to blow up if I put 0 in there. So we are just going to ignore, right, 0, meaning let's not trigger Karen. Let's go to the next example. Y equals, again, 3x squared plus or minus, whatever, doesn't really matter, 2x plus 4 square root of x minus 3. I have 3 functions combined in this case. So what am I going to do? Well, maybe I can even stuff this and call it a polynomial and call it one function. but I also can do individual parts. I'm still looking for that domain, right? I want to know the domain. So, okay, this one, all real numbers. Any number goes. This one, all real numbers. Any number goes. Yeah, it's always a 1, right? What now? Well, the square root goes, I can't only have, this, and food can't touch. Okay, great. So now x minus 3 has to be larger or equal than 0. And this is, you move 3 to the other side, x larger or equal than 3. So the first two functions that are part of this big function are okay with everything. This one can only operate if you give it the number larger than 3. 3 or bigger. So when you combine all 3 together, the domain is 3 to infinity, the most restrictive one. That's it. So the most restrictive domain is the one, because if you pick 1, x equals 1, what's going to happen? You're going to plug in 1 over here, and you're going to get 3. Yay! You're going to plug here 1. You're going to get negative 2. Yay! And then plus 4 times, you plug in 1 there, you get square root of negative 2. And there goes your neighborhood, right? You see that? Square root of negative 2. Bad value. It's not in the domain. That's why it's not in the domain. Domain starts with 3. So any number you pick, 3 and bigger, everyone's happy. If you pick a number smaller than 3, you have to deal with Karen right there. And Karen is going to make your life miserable. So I hope this all made sense. And this is where we technically use our combinations of functions, mainly to find the domain. We don't necessarily break this into multiple functions and think of the different. I mean, there are other instances when you compute values and compute numbers where it's very helpful to have factors, right, which is multiplication of functions. That's going to be eventually in calculus when you do first, second derivative tests and so on to test the signs. But there is not that much importance. As I said, about 99.9% of the time, you just care about the domain, and you can use it very successfully to figure out the domain of these functions that have multiple parts to it. Now, the title, function composition. That's the one that we really care about and want to learn about. So this is the major topic because it is combining functions by plugging one function into another function to create new function. Now this concept you are familiar with in your what you would call everyday life, and you use it every day, every hour, because you are going to combine multiple objects with or individuals with different functions together. My favorite example for this is always the backpack. So backpack has function to hold objects. I did not specify what those objects are. I just said the function of the backpack is to hold stuff. You might also say, well, the function of the backpack could also be to look nice as a fashion statement, and so sure, yes, as the accessory, right? But I don't think that you would really drag around empty backpack just to look cool. You will at least put something in it. Right? I don't care what, but just like one item at least. So see, backpack has a primary function to hold objects, stuff. Now, the purpose of the backpack is not really well defined until you plug in stuff in it that has particular function. So, put the books in. See, books have a function, right? When you read them, you learn. You can also use them to stack them up and prop yourself to get something off of the shelf, right? A lot of functions to books. But primarily, hopefully, right, read the book. So once you put that book into the backpack, it becomes the book bag. And you know you're going to maybe school, right? Hopefully school, whatever. So now your backpack became a book bag, school bag. And then you go home and it's weekend and you empty the books out of your backpack and you put in pots and pans and tent in it and you go hiking. Okay, the backpack now has a completely different purpose because now it's a backpack, right, for hiking. All of the stuff for hiking is in it. You can pack a parachute. It has the entire backpack has a completely different objective because you're definitely, hopefully, not going to jump out of the airplane with a book bag on, right? You pull the handle and the books come out flying. That's not going to end well. So you want to have the parachute, which has a function to keep you from slamming into the surface of the planet too quickly. So the parachute has a function, and that parachute is the stuffed into the bag that has a function to hold stuff. And now together, those two functions stitched together, where one function is stuffed into another function, literally in the physical world, you are creating a functional parachute bag, right? That you strap yourself in and then you jump out of airplane and hope for the best. So function composition is all about plugging one function into another function. So we have a notation for that. F composed with G of X, right? That's one notation. And this is not O. This is a circle. See, if I am to write fog, my O and G are the same height. When I write F composed with G, O and G are not the same height. So there is your little bit of your notation OCD if you want to do these things properly. Another notation is F and the G is plugged inside. You know how you write F of X? Well, now you don't write X. You write G in there. So now I hope that this particular notation here, which is what we primarily used, I hope that it's clear that you are plugging the entire function G inside function F. And there is a very nice way to say this. Every X of F is replaced by G of X. And that's your function composition. So let's build up to it with an example. F of X is equal to X squared plus 3 square roots of X. There you go. And g of x is equal to whatever. G of x is equal, I don't know, x plus 2, whatever, doesn't matter.
Well, that's exactly what I was thinking.
Yes, scary, right? Scary.
I was thinking 2x, so same variables.
Well, there is actually something to it in calculus, but it's way too early for that. Not early in the day, early in the mathematical development. Anyway, are we all cool with f of 4? Are we all cool with this?
Yeah.
Okay, so help me over here. What should I write?
4 squared plus 3 root of 4.
Beautiful. And we can just get our 16 plus 6 equals 22, and everyone happy. So I hope that we are all, I don't know why I went all shush about it. There you go. Now you can see it. So 4 squared is 16. Square root of 4 is 2. 2 times 3 is 6. 6 plus 16, 22. And we should all be very comfortable with this. This was lecture number 1. Computing value of the function. You also had this in algebra class. So 100% of students should be okay with this. No questions asked. Great. What's f of a flower?
You would replace all the x's with the flower.
Beautiful. It's a flower squared plus 3 square root of the flower, whatever the hell that means. We can do it. Remember when I said before, right? There are things that we can do it and we don't. Well, you just witnessed one of them, right? Perfectly fine. I could have used triangle, I could have used heart, right? Whatever. So, there you go. So, what if I just say this? What should I
You're
write?
replacing, you'd be replacing x with g of x.
Perfect. That's all it is. And can I now plug in what g actually is? It's x plus 2, right?
Yeah, I forgot we did that.
No, but that's the next step. I need your step. That is the first thing that should be obvious, because that is the same principle that we had before with number 4 and the flower. So whatever is here, as you can see, gets replaced for x. If it's x, it's x. If it's 4, it's 4. If it's flower, it's flower. And if it's g, it's g across the board. So there is no difference conceptually. This is where the people that would just observe the patterns and know nothing about mathematics would do better than someone who studied mathematics for 13 years like you did, right? Because technically, if this is your, right, you had 4 years of high school and eight grades prior to that, so you technically like study mathematics for 12 years. So this is your 13th year of math education, let's say. I don't need you to learn math over here. I want you to see a pattern of replacement. If I have x's, I have x's. If I have flowers, I have flowers. The rest of the structure of the function remains the same. So now I can plug in g of x the same way. So if you are getting this lecture is over for you, because that's the only thing you need to know. You are plugging one function into another function, and we're done.
Is what's written at the bottom, would that be the final answer?
Nah, you're going to do the thing. Right. Just make it
Ugh, I would always mess that up in algebra. That was the worst.
oh, the middle term. Yeah, the
Yeah,
grade
I would always
slayer.
forget about that.
Yeah,
Yeah.
I call this one the grade slayer. I have the names for all of those kind of things along the way. So the middle term for the binomial expansion, it's known as the grade slayer. All right.
It
Um,
fits.
yeah, it magically turns all A's to B's or B's to C's or C's to D's or D's to F. That's what the purpose of the middle term is. If you never figured that out in algebra, now you know. All right. So we have this very, very systematic procedure here that no matter what function is given to you, I don't want to talk about x squared and 3 root x. I want to talk about every function that you will ever see. Even, right, we talked about sine x, even though we're not supposed to, right? Can you tell me what the function composition is if I have square root of 3 over x over here? What is f of g of x? Using the function you have never seen before.
Would it be sine g of x?
Perfect. And then
Which would
you
be sine root 3 over x.
perfect. And you just did the function composition for pre-calculus 2, which is going to be 3 months from today down the line. And you just answer that question like it's nothing. And it's not because you are amazing with trig. It's because you are learning the concept that pertains to every function in existence. You don't need to know what those functions are, what they represent, how they look like on a graph, what their domain are. You need to know nothing about those functions. Every x of f gets replaced by g. It is that simple, that basic. That's all you need to know. Now, we are going to make this interesting and spicy, right? By let's talk about the domain. Let's see this. Let's see this. Let's see the other way to compose, right? G composed with F, meaning G is the boss, F gets plugged in, right? For whatever reason, now you're going to wrap your backpack in a parachute, right? I don't care why, but you're doing it, right? So when I so in this case, right, every x of g gets replaced with f. And it's again that simple. And if you are disappointed, I'm sorry, but that's all it is to it. So over here, we're going to say every x of g gets replaced by f of x. So if I go and say f of x equals, again, 3x. I don't know why I always go with 3x squared. How about 6 over x minus root x, and g of x is equal to 4 minus x squared. Compute f of g of x and compute g of f of x. And this, what you see here, is your standard exam 1 question, standard homework question, standard, right? And then I will show you where it pops up and how often, because remember, I can travel through time on this tablet. So let's see. What do we get for the F1 up there?
You'd get 6 over 4 minus x squared minus root of 4 minus x squared.
Mm-hmm. And before anyone says anything, there is nothing you can do here. You can look at it and cry. That's one thing, but you cannot simplify this. You cannot take square roots of 4 and x squared because there's a minus in between. You can take root of this, but you cannot take a root of that. So good. Now how about the G one? How about the G one?
It would be 4 minus the f function 6 over x
Okay.
minus root of x squared.
Nice. Now this one, my tablet is overheated even with with the high spec underneath. As soon as you see it go like this. Anyway, so now this one we can actually simplify. 4 minus 36, parenthesis, 36 over x squared minus 12 root x over x, and then plus x. And now put the largest term first, which is negative x. Then the next one is 4. And then these division terms, yeah. You don't have to, but it's nice if you do. There we go. Order of decreasing powers. This is a power of 1, power of 0, and now you have negative 1/2 power and negative 2 power. So they are in order of decreasing powers. It's called OCD in mathematics.
Wait, the powers have to go in decreasing order?
That's some kind of unwritten rule, right?
Yeah,
They
yeah.
they don't have to. It's just nice if they do, right? Everyone likes you better in mathematics if you do it, but you don't have to.
Yeah, I think we used to get points off in high school when if they weren't in
Depends on the level of OCD of your teacher. Yes, I'm not really going to knock off points, but I'm definitely going to like you better. Think about that. I can't. I mean, your grade doesn't depend on how well of friends we are. It's just you have the problem right or you have the problem wrong. But the idea is that this is a cool person. Look, it's a decreasing orders, and I'm all excited, right? Because I
there.
see decreasing up. It's just such is life. That's how the world works. Now, guys, we're not done with this because we're just going to now talk about the domain, right, of these functions, because the function composition is creating a new function which could have, um, which is probably going to have a different domain than your input functions, and that makes sense again by thinking, there are certain things that I can't actually stuff in the backpack, and then there are certain things that I can stuff in a backpack. So the domain of the backpack is all the stuff that you can put inside. Great. What can I put inside? Well, I can put my books, I can put the parachute, I can put the camping equipment, I can put change of clothing if I'm going for a sleepover for like one night or something, right? So you can do a lot with the backpack, and there is a domain of things, right? What are the things you can't stuff in it? Well, the moon, right? The Falcon Heavy, rocket from SpaceX, right? So there are a lot of other things. A bulldozer would not fit in your backpack. Your car, unless it's Prius, then it does. So there's a lot of things that you can't fit in the backpack. That just means that they're not in the domain, right, of the backpack. You can't fit them inside. Now, the output of the backpack is the actual purpose of the entire backpack once you put something in it. So what is that backpack for? So you go and say, oh, I put a parachute in it. Okay, I can jump out an airplane. So now your domain of activities that you can participate in includes jumping off of the buildings, off of the cliffs, and out of the airplane because you have a parachute. Not that I would recommend any one of those, but it's in the domain of possibilities of what you can do because the output of the backpack is going to be a parachute and you're hopefully safe, right? But then I can change the domain of the possibilities of what I do with the backpack by changing what I put inside. So now I put the books. See, jumping out of airplane is no longer on the list of preferred activities with that backpack because the book is not going to soften your landing. So what we see here is that you carefully look at function g of x, and you immediately notice that the domain is all real numbers. Literally anything goes. Anything goes. But then you also have a function g here where you enhanced it, right? You enhanced it with your function f. Now look at its output. All of a sudden, x can't be 0. So we managed to exclude the value. It was perfectly fine to plug in 0 here. 4 minus 0 is just 0. It's 4. So it works. But once I combined and plugged in f into g, it changed the function enough to change the domain. So now these things are important because later on in sciences you will have to link formulas together. If you already took either rudimentary physics, you know that, oh, if we combine this formula with this formula, yeah, you're now combining functions. And that changes domains. And you have to be careful with certain things, right? So there is a lot of stuff that you guys will practice for homework for these. And I would love to start the next class from, starting with your questions. These two sections are insanely important, and the next one coming up, 1.8, insanely important section. I'm hoping that you will have lots of good questions from these two, and especially if you're when you start looking at those problems that are using graphs. Maybe I can give an example of that, even though I hate giving examples so that you can follow example and try to memorize how to do the problem. But there is a valuable lecture. Let me see if I can find one of those in the book. And I frequently have questions from students stopping by asking, what the hell is going on over here? Why do I have all these graphs and all of these letters? So let's see. Now we need a large amount of OCD here. It's not gonna work well otherwise. Let's see how well I can do. So we have an absolute value shifted left 2 units, and that one is blue. Okay, And I have a red function which is negative x minus 4. Okay, so that's going to be parallel. That's my red function. Good. They say the blue one is y equals f of x, and the red one is y equals g of x. So as you know, just a different function for the letter f and letter g, but they both produce y values coming from x values. All right, so a question says, how much is f composed with g of negative 1? Now, the way you should understand this is f and then g computed at negative 1. Okay, that means that it's f of, and now I have to figure out how much is g of negative 1. Well, g is a red one. Negative 1 is right here. So that actually gives me negative 3. And now you answer your question by figuring out how much is f of negative 3, which is right there. So that's 1. Hey, the answer is f composed of g at negative 1 is 1. And if you plug in 1 into your MyMATLAB homework, it is going to say fantastic. So you chase these values on the graph. Now I hope that you picked up that the output of G is input for F, and they're linked that way. So G has its output of G has its input of negative 1. So that's where the world begins, right? G computed at negative 1. And the output of that calculation is negative 3. Because the red line, right, when you use red line to compute negative 1, we see that it bounces into negative 3. So output of G of negative 1 is negative 3, so I'm replacing entire G of negative 1 with negative 3. And then I just have to compute f of negative 3, and we are back to our lecture number 1, day 1, right? So you go to the blue line, find where the f of negative 3 is, and the y value for negative 3 when you bounce it off is positive 1. And woohoo! This is problem 91 in a textbook. Same graph, problem 92. F of g of, you know what? I'm going to ask you to do it. I'm going to delete these values that I had, and I'm asking you to solve 92. 92 says, oh, sorry, not 90, 92, 94. 94, 94. Same graphs, but this one is G composed with F of negative 1. So I had F composed with G. You have G composed with F. Any answers, possibly?
I got -5.
Yep, that's it, -5. -5. So we chase the values. We first write this as g of f of -1. So I just need to figure out how much is f of -1. Well, f is the blue one, and -1 is here, so boom, it's 1. So I just need to figure out how much is g of 1. So g of 1, that's the red one, right here, -5. Awesome. So you should have some of these problems to chase on the, as you can see, it's very easy to put these problems anywhere, homework, exams, and they show that you actually are able to follow this. Now, when you, like, are you learning this just to get your grade? Hell no. This is going to be the major pillar for chapter 3 and chapter 4 for a calculus 1. I have over here power to travel through time. So when I jump through time, and this is calculus 1. The tablet is overheated, so it's I am reviewing function composition just in case some poor soul didn't get the memo. You see all of the stuff that we talked about, except I have a lot of trig functions and exponential functions. We didn't get that. Talking about decomposing functions and so on. Every single one. Look at this function composition here. That's 3 functions combined together. And you can follow the chain the way, see, this x squared, which is h function, you stick it in there and you get your sine x squared. Then you take the whole thing in here and you stick it in there and you get your sine cubed x squared. So this function that you see is a composition function of 3 functions. How many can you compose? As many as you need to. So these are some concepts that they're not leaving. They're not going away. Here is the function of g of h, a triple composition. Now we're going to talk about it next class. I didn't want to dump everything in one sitting, but the function composition will then give rise, and then we start with calculus. But I did spend at least 30-40 minutes talking about what we talked in class, because there is no way to understand anything or do anything in this section or the rest of the calculus 1 course if you don't know function composition. So again, you are not learning these things to pass the test. That's meaningless, pointless waste of time, right? Because you can pass your pre-calculus test guaranteeing not to pass anything later, right? You have to learn this stuff to know it. And I hope you will have lots and lots of questions. We're going to review all of this next time, and then do that 1.8 section, which is going to end this trifecta of the most important lessons of all pre-calculus, 1.6, 1.7, and 1.8, which will be always used down the line. See you in 2 days. Bye.